So I'm going to prove this lemma that we used last time in the theorem that you see on the right, arguing the implications C implies A. And this is a theorem characterizing splitting fields. And this proof is rather nice, so I don't want to actually go through it. It says that if you have any algebraic extension K over F, you take any embedding from K to K, fixing F pointwise, then sigma is actually an isomorphism. Embedding means injective homomorphism of fields. So injective homomorphism of rings. But when the domain is a field, any non-zero homomorphism is automatically injective because fields don't have any non-zero ideals, you see. So what you're saying is that any non-zero homomorphism from K to K that fixes F pointwise is automatically an isomorphism. So it's an automorphism of the field K. It seems very strong. So to argue this out, I need to recall this embedding lemma, or rather, actually, I need to recall a little observation that we made while proving the embedding lemma. But here's the statement anyway, because this sort of is key to lots of things, so it does not harm recalling this. The only difference is that what I'm calling I here was earlier called sigma, but I don't want to confuse that with this sigma that's appearing in our lemma now. Okay. So what you have in the embedding lemma is an embedding from a field F to a field L called I. And what you're asking is, when can I extend this embedding to a bigger field that looks like this? So you have some irreducible polynomial, and you can go to this field fx mod p. It's an extension of f. What I'm asking is, when does there exist a sigma from K to L whose restriction to f is I? And the answer is, if and only if the polynomial that you get by applying I to this polynomial has a root in L. So I'll write down, there exists a sigma from K to L such that its restriction to f is I, if and only if the polynomial IPX has a root in L. And the reason for this is rather straightforward, actually. You notice that K is obtained from F by adding a root of this polynomial P. So this is some root of Px. So this A satisfies, in particular, A satisfies P of x. So if you had such a sigma, where would this A go? So let's write this sigma, let's write this polynomial as some Cj x to the j. So what you know is P of A is 0. Cj A to the j is 0. And you apply sigma to it if there was a sigma. Assume it exists, like up there. Then, first of all, it's a ring homomorphism, so you can break it up like this. Ca to the j, but then the power also breaks up, so Ca to the j, not C, sorry. Sigma. And then sigma of Cj is just I of Cj. See, because sigma restricted to f is just I, and these Cj's live in f. But this is nothing but the polynomial Ip evaluated at sigma A. So what I'm saying is, if A satisfies Px, then sigma A satisfies IPx. That if this is 0, then this would be 0 too. And now in the special case, when I is an inclusion, let's see what this is saying. Inclusion. So here L is actually sitting in F. When you have an inclusion, then you just IP is just P, because the map I is just identity on F. So then you're just saying that if A satisfies Px, then any such extension, for any such extension sigma, sigma A also satisfies Px. So what you're really saying is that if you have extensions like this, K and L, and A is something here, root of Px, then where it goes under any, if you take any embedding from K to L, fixing F point-wise, then where A goes is again a root of Px. Okay, so root of a polynomial has to again go to a root of the same polynomial as long as these guys satisfy polynomials over F. This is what I'm saying here. If you have two extensions, K and L of F, you have a A in K which satisfies some polynomial with coefficients in F, I should say Px in Fx, then for any sigma bar going from K to L fixing F point-wise, A would go to another root of Px again. Okay, so armed with this, let's see why this lemma is true. So I have K over F, and I have a embedding from K to K called sigma. So take some A in K. If it's already in F, I have nothing to do, so I'll take it outside F. And let Px be its minimal polynomial. This is an algebraic extension, K over F. So it has a minimal polynomial, be the minimal polynomial A. The trick is to look at some, so this extension as such might be infinite dimensional, but I can look at the subextension which contains all the roots of this polynomial, and that would be a finite subextension already containing A, and I want to look at that one. So let M be the subfield of K obtained by adjoining all roots of Px in K that are available in K. A was one of them, so I'm certainly going to add A, but if there were other roots of this polynomial in K, I'm going to add them too. So M is obtained from F by adding a bunch of roots of a single polynomial. So finitely many algebraic elements. So this extension is finite. That's going to be crucial. Let's restrict this sigma to M and see what we get. You see, if, what do I want to call it, B maybe, let B be any root of Px in K. So this B is in M. These are the things that I'm adding to F to get M. But then B satisfies Px, so sigma B also satisfies Px, is also a root of Px in K. But I added all the roots of Px in M already. That was the definition of M, obtained by adding all roots of Px in K. So by definition of M, the sigma B is again in M. So what you're saying is that M is F adjoin a bunch of these b's. One of them is actually a, finitely many. These are the roots of px that are available in K. And for each of these guys, sigma of bi is again in M. Right? Because they also satisfy the same polynomial px. So these roots just get permuted. But that tells you sigma of M is in M. So sigma restricted to M is actually a linear, injective linear map from M to M. Is a linear, it's a field homomorphism, but it's after all a linear, F linear map. It's an injective F linear map of this finite dimensional vector space to itself, of from M to M. But now I bring in this theorem from finite dimensional vector space theory that any, since this is the punchline, M over F is a finite dimensional vector space, over F, any injective linear map, linear transformation, is already surjective. Because if you have, just by looking at dimension really, if you have an injective map, then sigma M is isomorphic to M, so it has the same dimension as M. But if, so this has same dimension as M, but if you take a 15-dimensional vector space, any 15-dimensional subspace is automatically the whole vector space. Okay. So sigma from M to M is an isomorphism. But what does that say? In particular, A is in the image of sigma. So we started with any element in K minus F, and now we showed that A is in the image of sigma, so sigma is onto. And this essentially gives us the main implication in this theorem on the right, that an extension is a splitting field of a family of polynomials in Fx. K is a splitting field for a family of polynomials if and only if any embedding of K inside the algebraic closure F bar containing F and fixing little capital F pointwise is actually an automorphism of K. So we'll have reason to use that later on. Okay, now we're going to take a pause from this general development and talk about finite fields for a little bit, and then get back to it again.